So our second speaker today is Roberto Ignacio Genovese from the Barcelona Supercomputing Center, or BSC. He's a senior research engineer in the validation team in computer sciences. The topic of his talk is reusable verification environment for a RISC-V vector accelerator. Roberto is a research engineer at BSC. He received his Master of Science in Electrical and Computer Engineering degree from Portland State University in the USA in 2020 as a Fulbright scholar. His research interests include digital design verification methodologies and high-performance computer architectures, and he's located in Germany. Over to you. Thank you, Roberto.
Okay, thanks a lot for your presentation. Today, I wanted to share with you some insights of our work at BSC regarding the verification of multiple vector accelerator units, which implements the vector extension of the RISC-V ISA. Here at the BSC, we are a team working with RISC-V cores and accelerators. For those who are not familiar with RISC-V, I wanted to give a short introduction. RISC-V is a free and open source ISA with no royalty fees, and it's growing rapidly with open collaboration and being adopted for many applications like cloud, IoT, HPC, etc., across many industries. And it provides a modular ISA that it enables implementations that suit specific applications by adding capabilities to the base ISA with extensions. One of these extensions is the vector one. The vector accelerator unit that we have developed at BSC implements the version 0.7.1 of the vector extension, and we are now in the process of updating the RTL and accordingly the verification environment to support the version 1.0 of this extension. These accelerators are used in many projects across the BSC, and in particular, I would like to share with you two of them. One is for the EPI. This is the European Processor Initiative, which is a project currently implemented under the second stage of the Framework Partnership Agreement signed by the consortium with the European Commission, and whose aim is to design and implement a roadmap for a new family of low-power European processors for extreme-scale computing, high-performance big data, and a range of emerging applications. And another one of these applications is for a processor, which is a project that aims to build a new open-source out-of-order processor and deliver the first completely open-source European full-stack ecosystem based on RISC-V. Both of these projects are funded by the European Union. As you can see in this image, the superscalar core communicates with the VPU, the vector processing unit, through an interface, which is key in our verification approach, as this interface is the one that the verification environment will implement, exercise, and use to drive vector instructions to the VPU. Even though these units are similar and have the same purpose, that is processing vector instructions, they differ on how they communicate with the scalar core that we saw in the previous slide. And also in how they communicate and access memory, among other things. For API, the European Processor Initiative, the core communicates with the VPU using OBI. That's the interface that's shown in this image. The core is developed by Semidynamics. It's called Avispado. This interface, OBI, has a series of sub-channels, like we see in this image, for example, the issue, the dispatch, the completed, and so on. And the particularity of this interface is that the VPU access memory asking the core, sending requests to the core. So the core is the one that actually accesses memory and handles the memory requests coming from the VPU. For a processor, on the contrary, here we see the interface that communicates with the core. And the particularity of this VPU is that it communicates with the memory directly through a number 5 CHI interface. This adds the complexity of handling memory aliasing units in the verification environment. So here's an image of the previous verification environment that we had for verifying the VPU for the first version of EPI. Here we can see that we have, well, the environment is implemented using UVM, and it has a different agent for every channel of the interface. The problem with this implementation is that it entailed massive inter-process communication between the agents, as information regarding fetched, dispatched, in-flight, or completed instructions was distributed among them. That is, the interface implementation was not encapsulated, nor independent of other parts of the verification infrastructure, and it was really hard to maintain, debug when issues arise, extend, and reuse. Apart from this, we had other projects ahead involving the vector unit, like eProcessor, and the environment was not easily adaptable to it. Though we had many components in common, like test generation, coverage collection, continuous integrations, result comparisons, and the reference model. So after analyzing this, we came to the solution of having a base interface agnostic reusable verification environment, which needs to have the components shared among the projects, like the ones I mentioned, and a specific infrastructure dependent on each project, implementing the interface communicating with the core, which we decided to implement in a proper system Verilog interface. UVM allowed us to use object-oriented programming techniques for solving the issues that we have. In particular, polymorphism let us define pure abstract classes, which define methods common to all the projects, and that were implemented in the derived classes specific for each project. To do this, we created, as I mentioned, a base interface agnostic verification environment, which is called VPUDB, which has components shared and common to all of the projects, like the test generation, the reference model, etc., and a specific environment for each project with a specific implementation of the interfaces, the reference model, and some other specific configurations. The base interface agnostic verification environment, the VPUDB, provides a set of UVCs to generate vector instructions, reading them from binaries. This could be directives tests or tests generated with RISC-V. I will talk about this a little more later in the presentation. Send these instructions into the DUT, receive its results, and compare them with those of the reference model, which co-simulates instructions step by step. In our case, our reference model is Spike. So as I mentioned, for making the VPUDB interface agnostic, we created an abstract class, which is called a protocol-based class, which is instantiated in the driver and the monitors of the environment, that is extended in the project-specific environment, implements its methods according to the specifications of the interface, connecting the scalar core and the vector unit. Here we have the peer virtual methods that this base class defines, and that are called all across the environment. And here we can see an example of how the base interface agnostic verification environment communicates with the project-specific one. This example is for OVI. The protocol OVI interface is the class that extends the protocol-based class of the VPUDB and implements the methods that I showed before. Driving instructions taken from the test binary through the OVI interface to the VPU. Other methods collect completed instructions and the results and send them to the ISA scoreboard, which is a scoreboard that is common to all of the projects and it has checkers for ISA for the ISA. We have other scoreboard called the protocol scoreboard, which has specific checkers for the interface and is implemented in the project-specific environment. Regarding the reference model, polymorphism was also used to have the ability to utilize different reference models. In our case, as I mentioned, we use Spike. which is an instruction set simulator implemented in C++, and it's widely used across the industry and very reliable. And we communicate the verification environment to it using the DPI. That is the direct programming interface, which allows the communication between system variable and C++. Specifying a base abstract class, declaring the methods that we need from the ISAs, and implementing a derived class for the spike, which implements these methods, make replacing spike for another ISAs really easy. For example, we have made some tests using imperas. The base abstract class is then overridden by the desired one using the build in the build phase of the UVM test using UVM's factory capabilities. For example, we here can see the set type override by type. And also, as each specific project uses a different version of the spike, as they support different versions of the vector extension or different instructions, the ISS library file is project dependent, and a repository with different branches for each project is used to maintain, extend, and generate it. Regarding test generation, as each project implements different kinds of instructions, as I mentioned, or different versions of the ISA, the base verification environment has as a submodule a test repository, which includes a specific test for each kind of instructions and their different possible configurations, including vector length, single element width, etc. And this submodule branch is specified in the project-specific environment, so we can have different tests for each project. Also, we have random tests. For this, we use Google's RISC-V generator, which we have modified according to our needs for every project, supporting different instructions under constraints, configurations, CSRs, etc. These random tests are generated in the CI flow, specifying the target project. And the CI is accomplished using GitLab pipelines common to all of the projects, like sanity checks, random tests, merge requests, small and big regressions, etc. And these pipelines are also in charge of collecting functional and code coverage. And also they merge the result coverage databases from the regressions and generate an HTML report, which can be accessed via web. In particular, as I mentioned, we have already used this implementation infrastructure in two projects, one for API and another for eProcessor. The project-specific environment for API is called EPAC BPUDB. This environment implements the OVI interface connecting the semi-dynamic core with the vector unit. And the inherited do protocol function, which is declared in the protocol base class, calls a task for each subinterface of OVI. That is issue, dispatch, completed, memop, load, store, etc. This task read a queue containing vector instructions, which is filled by the drive method of the interface called in the base verification environment driver. And completed instructions are put in another queue, which is read by the environment's monitor calling the monitor post method, also declared in the protocol base class. The environment also has a specific monitor and a scoreboard for checking the correct behavior of the interface, as I mentioned, the protocol scoreboard. And also, it has a specific coverage for instructions supported only by this project and the OVI interface. Regarding Spike, this project's version performs memory reads and writes as needed for communicating with the vector unit, which relies on the scalar core for performing these operations, as well as for handling CSRs. Here we have an example of the folder structure of the environment, where we can see the base verification environment, the BPUDB. Inside of it, we have cloned the project-specific one, the EPAC BPUDB, and inside we have the RTL code. Also, we have the test folder specific for this environment. And here we have a GitLab pipeline showing a regression with ISA tests, where all of them are passing. Regarding eProcessor, as I mentioned before, for this project, memory is accessed directly through a number 5 CHI interface instead of receiving data directly from the core as in API. The interface communicating with the scalar core needs to send and receive information to detect and avoid memory aliasing between it and the BPU. And this functionality is implemented in the interface extending the base protocol class, of course. Regarding Spike, we had to make modifications in order to support other kinds of instructions like float point 8, 16, and AI. And also CSRs are handled in the vector unit, contrary to API. Instructions for reading and writing these CSRs, for example, the VZBL, VZBLI, CSR read, and CSR write, need to be sent through the protocol interface. And also we have added cover groups for these instructions that are specific for this environment. Here we have an example also of the folder structure for this project. We can see the base verification environment, the project specific one, the RTL, and the test folder, which is specific for this project. And again, a GitLab pipeline running a set of ISA tests. In conclusion, we can say that we have accomplished having a verification infrastructure. We can be reused, adapted, and extended to different projects. We have already proven it to work for 2 of them, and we are in the process of using it for upcoming ones like APSGI2, which implements the version 1.0 of the vector extension and a newer version of OBI. And by just developing the implementation of the interface, we have a working infrastructure for generating tests, feeding them to the design, compare the results with the ISS, running regressions, and detect bugs rapidly. In comparison with the previous verification environment, the new one has a faster compilation and simulation times, and it's very easy to maintain and extend. Also, we have been able to uncover more bugs not detected using the old environment as a result of better implementation with less constraints on the test cases generation and bigger test regressions. As I mentioned before, these 2 projects are funded by the European Union. And with that, I can conclude with my presentation. Thank you so much for your time.
Thank you very much. Thank you very much, Roberto. There are a few questions for you. That's it. Okay.
Yeah.
During the presentation, you mentioned instruction renaming. Can you explain what you meant by instruction renaming, please?
Sorry, instruction renaming?
Yes. Yes.
I don't remember having mentioned that, but I suppose it's related to the kind of instructions that we support for each one of the projects.
Okay.
We have a different set of instructions supported for each of the projects. So for this reason, we have different reference models. I mean, the same reference model, but with some differences in them. This is why we have to maintain separate reference model repositories for each project, as well as test cases generation. In this sense, we need to modify. We have to modify RISC-V, this tool that came from Google, and have also different branches for each of the projects with the specific instructions.
Okay, thank you. Is the code open source and available for downloading?
It depends on the project. These projects are developed by not just by BSC, but by BSC and other companies across the European Union. As I mentioned, for example, the core for API is developed by Semidynamics. So some parts of the code are open source, some parts are not. In particular, for eProcessor, the objective of the project is to have an open source full stack ecosystem, so it will be available for downloading.
Okay. And did you use functional coverage at all? And is there anything that's reusable from that functional coverage, please?
Yes. We have implemented functional coverage for the ISA, which is shared among the projects. And we also have shared among the projects also functional coverage for inner parts of the RTL of the VPU. And we also have developed functional coverage for the specific interface for each of the projects. So we have parts that can be shared and parts that cannot be shared.
Okay. Okay. And they're downloadable, did you say? Or not?
Yeah.
We can. That's shareable and can be downloaded and reused. Okay.
Exactly.
Okay. And another question: is there any plans for this? Is there what's the next step in this project? Do you have a sort of roadmap for this?
Yes, of course. We have a roadmap upcoming for many years. As I mentioned, we are now in the process of verifying eProcessor. The API project is, and for the API project, we are in the second stage of the project, implementing the newer version of the vector extension and the newer version of OBI. So yes, for them, we have things coming for many years.
Okay. Okay. So thank you very much. Just sorry, one more question is just coming. Which European project is this under? Is there a name for the European project?
Can you repeat that?
Is there a name for the European project we're part of?
Yes, it's the European Processor Initiative.
European Processor Initiative. Okay, and I presume there's other projects under that, correct?
Yes, of course.
Okay, and are they all mainly RISC-V or are there a range of different?
For BSc, it's all based in RISC-V.
Okay. 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 Thank you very much.
Thanks to you.
Thank you, Roberto. Thank you. So we're just waiting for Holger. We're running a little bit early, so we're just waiting for Holger to join at the moment. See if we can get him.
Hello everyone, I request you to please wait. We are waiting for Mr. Holger to join in.
Hello, please accept our apologies for the delay. I understand Mike is trying to contact Holger to see if there are any technical issues he has. Please bear with us. Mike, have you been able to reach Holger? Are we continuing with the DV Club?
Well, he's not due. No, I haven't got him yet, but he's not due to start to 2-3 minutes. So we'll wait.
Oh, okay, thank you.
Okay, I don't see Holger. Now and the time's come for him to start. So I think we'll just have to wrap up here. What we'll do is we'll ask him to record separately, and then we'll send out a recording of his paper. So, Disha, can I share my screen, please?
Yeah, sure.
Can you see that, Disha?
Yes, I can see the screen.
Okay, so apologies for not having a third speaker. We did check with him this morning, but I don't know, he hasn't seemed to have arrived. We will try to get him to record it, but we do have the slides and recordings of the first two speakers. So thank you very much to both Lucas and Roberto. You'll receive a PDF of their slides and also a recording in due course. We will also put up a PDF of the slides from Holger for you to see, and we'll ask them to do a recording, and we'll put that recording up as well. If you've got any suggestions for DV Club events in the future, please send them to me. That's my email address. We do have some events coming up. We do have Verification Futures. This will be held in Reading on the 22nd of June, but there will be remote access. But if you want physical access in the UK, it's in Reading on the 22nd of June with remote access too. And we do have dates for DV Club on the 25th of April, the 5th of September, and the 28th of November this year. So keep an eye out for those. And then again, thank you to our speakers, Lucas Junga from Machineware GmbH and Roberto Ignacio Genovese from the Barcelona Supercomputing Center. And thank you to our sponsors as well, Ignacio, Cadence, Synopsys, Brecker, Impelas, ARM and ST, who are our hosts when we go back to physical events, and TESOL for organising the event. Thank you very much for your time. Thank you. We can end the event, please, Disha.
Yes. Thank you everyone
Thank you.
for joining for today's TV Club.